We now give an interpretation of the mutual information between x and y, where x and y are continuous random variables. We assume that the joint PDF fxy exists and is continuous. For a fixed delta, for all integer I and j, define the intervals axi equals the interval from I delta to I plus 1 delta, and the interval ayj equals the interval from j delta to j plus 1 delta, where axi is an interval on the x-axis and ayj is an interval on the y-axis. And then define the rectangle axyi, j to be the Cartesian product of axi and ayj. Accordingly, define the discrete random variables x hat delta equals I if the random variable x is in the interval axi, and the random variable y hat delta equals j if the random variable y is in the interval ayj. The random variables x hat delta and y hat delta are quantizations of the random variables x and y respectively. This is illustrated in the figure. Now for all I and j, let the pair xi, yj be a vector in the Cartesian product of axi and ayj. Now we compute the mutual information between the two discrete random variables x hat delta and y hat delta. This is equal to summation I summation j, the probability that x hat delta and y hat delta is equal to ij, times the log that x hat delta and y hat delta equals ij, divided by the probability that x hat delta is equal to I, times the probability that y hat delta is equal to j. In the next step, we approximate the probability that x hat delta and y hat delta equals I and j by fxij yij times delta square. This is valid because we assume that the joint PDF fxy is continuous. Similarly, we approximate the probability that x hat delta is equal to I by fxi times delta, and the probability that y hat delta is equal to j by fyj times delta. Then this delta square is cancelled by this delta, and so we obtain summation I summation j fxi comma yj times delta square log fxi comma yj divided by fxi times fyj. When delta is small, this is approximately equal to integrating fxy times log fxy divided by fx times fy with respect to dx dy over all x and y. And this is equal to the mutual information between the two continuous random variables x and y. That is, when delta is small, the mutual information between the quantized version of x and y is very close to the mutual information between x and y. Therefore, the mutual information between x and y can be interpreted as the limit of the mutual information between the quantized version as delta tends to 0. It can be shown that this interpretation continues to be valid for general distributions for x and y. Therefore, unlike the differential entropy, which does not carry any physical meaning, the mutual information between two random variables x and y carries the same meaning, whether they are discrete random variables or general random variables. In definition 10.28, we let y be a continuous random variable related to a discrete random variable through a conditional PDF fy given x. The conditional entropy of x given y is defined as Hx given y equals the entropy of X minus the mutual information between X and Y. Proposition 10.29 says that for two random variables X and Y, if Y is continuous, then the differential entropy of Y is equal to the differential entropy of Y given X plus the mutual information between X and Y. And if Y is discrete, then the entropy of Y is equal to the entropy of Y given X plus the mutual information between X and Y. We also have the chain rule for differential entropy, which has exactly the same form as its discrete analog. Theorem 10.31 says that the mutual information between X and Y is always non-negative and is equal to 0 if and only if X is independent of Y. As a corollary, the mutual information between X and Y conditioning on T is greater than or equal to 0 with equality if and only if X is independent of Y conditioning on T. Another corollary says that conditioning does not increase differential entropy. That is, the differential entropy of X given Y is less than or equal to the differential entropy of X with equality if and only if X and Y are independent. The proof of these results are very similar to the proofs of their discrete analog, and so they are omitted. We only have to make a couple of remarks. For continuous random variables, differential entropy and conditional differential entropy are not always non-negative. However, mutual information and conditional mutual information are always non-negative. Another corollary is the independence bound for differential entropy, which has exactly the same form as its discrete analog.